Okay, so imagine a rabbit, a very long, skinny rabbit that never dies, and it reproduces perfectly every single month.
A very specific kind of rabbit.
A very specific, very mathematical rabbit. Its population would grow following this exact pattern: 0, 1, 1, 2, 3, 5, 8, 13. And you know the rest.
Of course. The Fibonacci sequence.
Right. But this is so much more than just a math curiosity tied to a, let's be honest, completely unrealistic rabbit problem. This is an ancient fundamental rule. It secretly governs everything from, say, the computer algorithms running your life.
To the spiral on a sunflower. It's truly pervasive. You see it pop up in geometry, number theory, even high-level cryptography.
And for this deep dive, we're taking all your source material and we're going to trace this sequence from its deep historical roots all the way to its most surprising modern applications.
And our mission here isn't just to list where it appears. We want to understand the precise mathematical reason for its power, specifically its really intimate link with the golden ratio.
Okay, let's unpack that. First, the definition. A Fibonacci number, let's call it F sub nn, is just the sum of the two numbers that came right before it.
Fn equals Fn minus 1 plus Fn minus 2. Simple as that. You start with 0 and 1, and you just keep adding.
And as you mentioned at the start, that definition is usually tied to the Italian mathematician Leonardo of Pisa.
Sure.
Right, Fibonacci.
Yes, in his 1202 book, Liber Abaci, he introduced it to Western Europe, and the whole thing was framed around that idealized and, frankly, pretty silly rabbit problem.
The famous thought experiment. You start with one pair, they mature, and then boom, a new pair every month, forever. But this is where the history gets really interesting for me. The system of numbers is much, much older than the 13th century.
Oh, absolutely. While Fibonacci popularized it in the West, the sequence actually originated way earlier in Indian mathematics, possibly as early as 200 BC, in the work of a scholar named Pingala.
Wait, 200 BC? That's centuries before Fibonacci. What were they using it for back then?
Well, they weren't tracking rabbits, they were tracking poetry. Pingala was concerned with Sanskrit prosody.
Okay, so the rhythm of poetry.
Exactly. The patterns you can form from long syllables, which counted as 2 units, and short syllables, which were 1 unit.
So it was all about patterns of arrangement.
Precisely. The question was, how many different patterns of long and short syllables can I make to create a total duration of, say, m units? And the answer is exactly f sub plus 1.
That's fantastic. So this sequence was tracking poetic meters long before it was ever applied to population dynamics.
It just shows the incredible abstract power these simple rules hold.
Absolutely. Okay, let's shift to the mathematical core, because the real reason this sequence is so important. It hinges on one specific irrational number, the golden ratio, phi.
The golden ratio, phi, which is approximately 1.618 that is the absolute backbone of the sequence. The connection is, well, you can see it if you look at the ratio of consecutive Fibonacci numbers.
You mean if you divide one number by the one before it?
Exactly. You divide Fn plus 1 by Fn, and as n gets bigger and bigger, that ratio gets closer and closer to phi. It marches right towards it.
I know the astronomer Johannes Kepler noticed this centuries ago. He wrote something like, as 5 is to 8, so is 8 to 13 practically. It's an almost perfect relationship that just gets better.
And that's not just a cool observation. It's formalized by Binet's formula. This is the closed form expression. It lets you calculate the nth Fibonacci number directly.
Without having to add up all the preceding terms.
Right, which is a huge deal.
So, if the golden ratio is so dominant here, is there a simple math trick? A shortcut to calculate, say, the 100th Fibonacci number without running through the whole sequence?
Yes, and this is where the dominance of phi really shines. The full Binet formula actually uses both phi and its conjugate. We can call it tau psi. But the thing is, the contribution of that second term, the psi I term, it gets tiny, almost 0, as n gets large.
So the conjugate is just mathematical noise at that scale.
Exactly. For any large n, you can approximate the Fibonacci number just by taking phi to the power of n, dividing it by the square root of 5, and then just rounding to the nearest integer.
That's an incredible shortcut. It really shows how phi just completely defines the sequence's magnitude.
It does.
And this leads right into one of its most powerful computational applications. Matrices. I understand you can pack that relationship fk plus 2 equals fk plus 1 plus fk into a small 2x2 matrix.
That's right. And the beauty of that is, if you want the nth number, you don't have to iterate n times. You just raise that specific 2x2 matrix to the nth power.
Okay, so for those of us who aren't constantly powering up matrices, why is that useful? Why is raising a matrix to a high power better than just adding numbers over and over. Is this the big speed hack?
It is the speed hack. When you're calculating something like x to the power of n, you don't multiply x by itself 100 times. You use a technique called exponentiation by squaring.
So you're taking bigger leaps.
Exponentially bigger, you calculate x squared, then x to the fourth, then x to the eighth, and so on. You can get to a huge power in just a few steps.
Yeah.
Logarithmic time, we call it.
Which is vital for any algorithm dealing with very, very large numbers.
Precisely. And as a bonus, if you take the determinant of that matrix power, you get Cassini's identity, a beautiful, elegant equation that shows fn plus 1 times fn minus 1 minus fn squared will always equal plus or minus 1.
Always. That's incredible.
Locked in.
Hey, speaking of elegance, I love the combinatorial side of this, like how fn plus 2 is the number of binary strings of length that don't have consecutive ones.
It's a remarkable property. If you have 4 digits, so n equals 4, you get 8 possible strings, and 8 is f sub 6.
It's not just trivia. It means this number is the natural answer to some really fundamental counting problems.
In so many different fields.
Mind blown.
Oh.
Okay, let's move from abstract numbers to the physical world, because we have to talk about nature's obsession with this sequence. We have to talk about phyllotaxis.
Phyllotaxis. It's the arrangement of things like leaves on a stem, seeds in a sunflower, the scales on a pine cone. And if you look closely, you see spirals.
Spirals going in 2 directions, right?
One clockwise, one counterclockwise. And when you count them, the numbers are almost always adjacent Fibonacci numbers.
Like a chamomile head having 13 spirals one way and 21 the other, a pineapple with 8 and 13. I mean, the question is why? Why would a plant be running Fibonacci's algorithm? What on earth does 1.618 have to do with maximizing its space?
This is the absolute core of the deep dive. The optimal arrangement is driven by the golden ratio because of a really deep property from number theory. The fact that phi is, mathematically speaking, the hardest number to approximate with a rational number.
Okay, hardest to approximate. That's a very abstract concept.
Yeah.
How should we think about that? Is it like a scorecard for how stubborn a number is?
That's a perfect analogy. Mathematicians quantify this with something called the Lagrange number. It's tied to Markov's approximation theory. Every irrational number has a score, an LX that measures how easily you can find simple fractions that get extremely close to it.
And what's phi's score?
The golden ratio has the smallest possible score, the square root of 5. This means phi is the most stubborn, the most difficult number to pin down with a simple ratio. Any other irrational number is easier to approximate.
Okay, I think I'm seeing the connection to the plant now. If the plant used an angle based on an easier number,
one that's close to a simple fraction.
right, then the new buds would eventually land almost exactly on top of or right next to an older bud. You'd get overlap, you'd waste space.
Precisely. If the angle is, say, 2/5 of a circle, the 5th seed will land right back where the first one was. The system repeats. But by choosing the divergence angle related to phi, the golden angle, the ratio is so stubborn it avoids repetition and maximizes the space between every single bud.
So it's nature using the golden ratio as a defense mechanism against overlap. It picks the hardest number to approximate to guarantee the most efficient packing possible.
And the mathematical modeling confirms it. Researchers modeled this, defining a measure of growth capacity. Essentially, maximizing the area covered by the buds without them touching. And the rigorous proof, it's tied to hyperbolic geometry, guarantees this is globally optimal if and only if the divergence is the golden ratio.
The math guarantees it's the best possible packing.
It does.
That is just a phenomenal link between abstract algebra and functional biology. Okay, let's pivot away from nature and look at some highly functional applications for you, the learner, in the world of computing.
Well, the sequence is fundamental to runtime analysis in computer science. A great example is Euclid's algorithm.
The classic method for finding the greatest common divisor of 2 integers.
Exactly. Now, engineers need to know the worst-case scenario. What are the inputs that take the absolute longest time to process?
And let me guess.
It turns out the worst-case inputs for Euclid's algorithm are always 2 consecutive Fibonacci numbers. The number of steps the algorithm takes is directly proportional to how far out in the sequence you are.
So they're a tool for stress testing, a foundational algorithm.
A perfect one. And they're used directly in data structures, too. The Fibonacci heap, which is critical for some highly efficient graph algorithms, gets its name because its performance analysis relies heavily on these numbers.
And there's an optimization technique too, right? The Fibonacci search.
Yes, it provides a very efficient way to find the minimum or maximum of a function over some interval.
It's fun to note too that even non-math fields borrow this structure. Agile software teams use a modified Fibonacci series, something like 1, 2, 3, 5, 8, 13, 20.
Right, for planning poker.
They're borrowing the structure because as the numbers get bigger, the gaps between them also grow. It represents the increasing uncertainty in larger estimations.
It's a great example of the structure being useful for organizational psychology. Shifting back to pure math, though, the sequence has all these number theory fun facts.
Like Fibonacci primes,
Yeah.
we know the first few, 2, 3, 5, 13, 89, but it's one of those canalizing mysteries. Nobody knows if there are infinitely many of them.
And the properties around squares are incredibly restrictive. I mean, you have an infinite set of numbers, but the only non-trivial square Fibonacci number is 144, F12.
It's like the sequence fights against forming those perfect shapes.
It does.
So it seems like such a singular special structure. But really, the classic Fibonacci sequence is just one member of a huge family, isn't it?
Absolutely. It's a specific instance of a much broader concept.
Right.
The generalized Fibonacci sequence.
Which has the same recurrence relation, but you can change the coefficients.
Exactly. Vn equals p times Vn minus 1 plus q times Vn minus 2. You can adjust p and q, and you can pick different starting points.
So you get a whole zoo of related sequences that share the same underlying structure.
Right. For instance, the famous Lucas sequence starts with 2 and 1, but it uses the same p and q as Fibonacci. But if you change the coefficients, you get even more different sequences.
Okay, give us an example. What happens when you change the coefficients?
Look at the Pell sequence. Here, we set p equal to 2 and q equal to 1. We start with 0, 1. The sequence goes 0, 1, 2, 5, 12, 29. It grows much faster.
So if the Fibonacci sequence's magic comes from converging to the golden ratio, 5, what does the Pell sequence converge to?
It converges to 1 plus the square root of 2, about 2.414.
Sometimes called the silver ratio.
The silver ratio. And just as phi is linked to the geometry of the pentagon and approximating root 5, this number is fundamentally linked to approximating the square root of 2.
So that structural similarity is the real takeaway here. The principles we've been talking about, they apply to this whole family of sequences.
It proves the mathematical power lies in the structure of the recurrence relation itself.
So we've gone from ancient Indian poetry and 13th century rabbits all the way to high-speed matrix computations and proving why a sunflower looks the way it does. What stands out to you as the core unifying idea here?
I'd say the power isn't mystical, it's quantitative. The reason it appears everywhere is its direct link to the golden ratio. And the reason the golden ratio is so essential is that one unique property, it is the number least well approximated by rational numbers.
Which turns out to be nature's perfect strategy for dense, non-overlapping packing.
Exactly.
So if that core property, being the hardest number to approximate, drives the best solution for growth on Earth, it makes you wonder about the alternatives.
Indeed. We know the golden ratio is mathematically optimal, but that same Markov theory suggests that if some exceptional or maybe extraterrestrial growth scheme were possible that wasn't tied to phi, the next most mathematically optimal arrangement would be tied to 1 plus the square root of 2.
Silver ratio.
The one linked to the Pell number. So it makes you wonder, what other phenomena, maybe outside of our common observation, might be secretly governed by these other mathematically optimal structures, just waiting for us to notice the pattern? That's something worth digging into.